Vectors, on the other hand, are quantities that are only fully described if we provide both the magnitude and the direction. Vectors include velocity, displacement, acceleration, momentum, force, lift, drag. You get the idea. Since vectors have both magnitude and direction, we can describe them by drawing arrows.
Here's a very brief look at the addition of vectors. I just grab one of these vectors and drop it anywhere on the screen. I can change the length of the vector, I can rotate it. And every time I do that, I am changing the vector. The vector is defined by its magnitude and its direction. However, if I pick up the vector and I drop it somewhere else, I'm not changing anything about it. I haven't changed the direction or the magnitude. If I drop it at the origin, in other words, in standard position, again, measuring the angle from the positive x-axis up to the vector, and now at least it's easier to see. We can see that this is a quadrant 1 vector. Up at the top, you can see that the magnitude of the vector is given. This vector has a magnitude of 12.2 units, and it's directed at 35 degrees. What other information is given about this vector? This is vector A, so A subscript x is the x-coordinate of the vector, and A subscript y is the y-coordinate. The x and the y coordinates of the vector are just projections of the vector onto the axes. This looks like this. For our current vector A, the x component is here along the x-axis, and the y component we draw up to create a right angle triangle. That means that we can use trigonometry to find the values of the x component and the y component. We can add vectors in a number of different ways. Not worrying about putting those vectors onto the coordinate plane lets us add vectors. Lets us add vectors that look like this. Here are two vectors. I'll just create two different ones, and we can add them by what we call the polygon method, which is just to organize the vectors tip to tail. The sum of those vectors is then drawn starting at the beginning of the first vector and ending at the end of the last vector. It does not matter which order we add the vectors in. You can see that the sum does not change if I start with vector B and then add vector A. I can even add a third vector to the mix, or a fourth vector. If I have vector C, I can add it to the end of where I've left off, and you'll see that the sum starts at the beginning of the first vector and ends at the end of the last vector. Essentially, we can think about walking along the light blue vectors, going the long way around, going almost completely north, then very much northeast, and finally directly south. And the sum of those vectors just represents where we've ended up in relation to where we've started. The sum of the vectors isn't interested in the route we took to get there. Another way to draw the addition of vectors that works very well for two vectors looks like this. I'll take vector A and vector B, and now I'll imagine that these two vectors make up two sides of a parallelogram. So I'll draw in the other two sides. I'll sketch in the other two sides of the parallelogram, remembering that the top and the bottom of a parallelogram are parallel, as are the left side and the right side. Now we'll find that the sum of the two vectors is the diagonal of the parallelogram. I didn't draw the parallelogram all that nicely, so it wasn't perfect, but there we have it. That's a nice method for adding vectors when you've decided already to draw both vectors starting at the origin. Let's put them there. So if vector A and vector B are both drawn at the origin, you can see that the sum of the vectors is longer than either of the two original, but it's still in quadrant 1. To add vectors algebraically, we're going to rely on the components of the vectors. So let's take both vector A and vector B and resolve them into their components. I'll draw a slightly different vector B so we can see its components more clearly. So let's add vector A and B. If we use the polygon method, it would look like this. And the resultant would tuck in neatly here, starting at the beginning of the first vector and ending at the end of the second vector. What do you notice? Well, here on the resultant, I also have an x component and a y component. In fact, the x component of the resultant is the sum of the x components on vectors a and b. The y component of the resultant is similarly the sum of the y component of vectors a and b. So this is going to be true regardless of which quadrant we're working in. We can look at a couple more examples here. If I take vector b and it turns out that vector b put at the origin is actually in quadrant 4, you can see quite clearly that if I add vectors a and b, my resultant is also going to be below the positive x-axis, or also in quadrant 4. In this case, you can see that looking at the x components, vector a has a positive x component, as does vector b. In fact, if I highlight those vectors, you can see that more clearly. Vector a has a positive x component looking at this top bar. Selecting vector b shows that its x component is also positive. Vector a is in quadrant 1, so it also has a positive y component. If I select vector b and again look at this top bar, I now see a negative y component. Essentially, that 8 and negative 10 are the coordinates that my vector points at if I started at the origin. Because the x components of vector a and b are both positive, when we add them up, the x component for the resultant is longer than either individually. But for the y components, they largely cancel each other out. With a positive y component for vector a and a negative y component for vector b, albeit a slightly larger negative value, we end up with quite a small value for the y component of the resultant. And in fact, the y component of the resultant is negative. So with a positive x component and a negative y component, our resultant is in quadrant 4. So our steps for adding vectors algebraically will always look the same. Our first job is to take the 2, 3, 4, however many vectors we have, and resolve each into its x and y components. Then we add up the x components of the vectors to find the x component of the resultant. Then we'll add up the y component of the vectors to find the y component of the resultant. I'm sure you can imagine that if I have the x component and the y component for a vector, then I can use Pythagorean theorem to find the hypotenuse, which is the magnitude of the resultant. If I have two sides of a right angle triangle, I can also find the angle. I can use the inverse tangent of the y component over the x component to find the angle that the resultant is directed at. Notice that if I have a vector in quadrant 1, let's have a look at its components, and I look just at the components to determine the angle, then the angle that I calculate will be the correct answer. But imagining if I have a quadrant 4 vector, if I use the x component and the y component to calculate the angle here, I have to be aware that my calculator is going to give me a negative value, because it's going to tell me that starting at the x-axis in standard position, I'll find the vector by moving clockwise. Imagining a quadrant 2 angle or a quadrant 3 angle. In both of these situations, a calculator will only be able to give you the reference angle, the angle down from the positive, or rather down from the negative x-axis for a quadrant 3 angle, or up from the negative x-axis for a quadrant 2 angle. In order to find the value of the angle then, in other words, to find the value of the angle in standard position, you will either have to take 180 degrees and subtract the reference angle, or if your resultant is in quadrant 3, you'll want to take 180 degrees and add the reference angle. We'll see each of these pieces in detail.